In this lecture, I'm going to introduce you to multiple integrals. The motivation is to find the volume under a surface z equals f of xy and above some region r in the xy plane. And we want to begin by reviewing what we did in a similar situation where we had a curve y equals f of x and wanted to find the area below that curve and above some interval in the xy plane, or where x is between a and b. We imagine taking the interval for x and breaking it up into pieces and making rectangles underneath the curve. And as you can recall, the more rectangles you use, the better and better this approximates the area underneath the curve. So the idea is to take a lot of small rectangles, and with the thickness being very small, and to approximate the area underneath the curve, we want to add up the areas of the small rectangles. So I'm summing up the areas of the rectangles. I'm going to take the height of a rectangle and multiply that by the width of a rectangle. And I want the number of rectangles to go to infinity. And I'm imagining the width is also getting small as we do this. So the width of these rectangles is going to 0. So the height will be given by the value of the function f of xy here for some point inside your rectangle. And the width will be a small change in x, which we're denoting by delta x. So we're summing up a bunch of heights times their widths of these rectangles to get the area of the rectangle. And we let a number of these go to infinity. And again, the delta x gets small, then this is going to give us a value for the area underneath this curve. And we write this as an integral. The sum is replaced by an integral sign. The height f of x is still the same, and the delta x gets replaced with dx. And this integral represents then this limit that we have on the previous line as n goes to infinity, and also, as I said, delta x goes to 0. We want to do something similar when we're in space in 3 dimensions. We want to imagine approximating the area underneath some surface by looking at boxes underneath the surface and above the xy plane. And the more boxes we use, the better and better we approximate the volume underneath this surface and above the xy plane. So as we take the volumes of each of these boxes, we will take the height times the length times the width. So the height, you can see, is going to be a value of the function, the z equals f of xy here. The length is going to be a delta y, a small change in y, and the width will be a small change in x. And we multiply those together to get a volume of one of these boxes, and we want to sum over all the boxes and let the number of them go to infinity as well as the width and length going to 0. So again, the height will be a value of the function, the length will be actually the delta y here, and the width will be delta x. In the limit, what's going to happen here is the sum is going to be replaced by a double integral, and the delta x and delta y will be replaced by dx and dy, or what we'll call dA sometimes, but dA will represent dx dy or dy dx. And this just gets replaced with f of xy. So this is what we have. R here is representing the region in the xy plane that you're integrating over. In this case, it looks like a rectangle on the bottom there. And we have our height f of xy. The dA, again, is going to be dx dy or dy dx. We will sometimes write this like this. And the y range is going from c to d, and the x is going from a to b. And now we'll elaborate on that a little bit later, but the dy dx is just representing the dA. And the double integral, these limits of integration are just telling me what's happening with dy and dx. With the C to D being the dy, what's in the middle there, and the A to B being what's going on with dx. Here's a picture from a book, and you can see how they did. This region is not a rectangle anymore that's on the xy plane, but it's something else. But we're still going to go ahead and draw little rectangles inside here, or squares, and then we're going to make boxes. And so we have some picture like this of a box. This is just one of them, but we want to make lots of boxes, and this will be the delta y and delta x again, and the height of the box will be f of xy. And we want to sum over all these boxes, and that becomes this double integral. Here's another picture from a book. And there's one of the boxes again. Here's a perhaps better picture from a book. Again, we have a little rectangle on the bottom. That's what this is representing. And we are taking the area of that rectangle, delta y times delta x, and multiplying it by the height, which is a function of f of x, y. Here's another picture from a book. And here's a definition of the volume, but this is what you want it to be. It's the sum of the values of the volumes of the rectangles, and where they n go to infinity. And again, you want the piece of the area also to be getting small here. So this is delta x, delta y, or delta y, delta x. So let me do some examples. Here's the first example. And for these examples, all we know at this point is that this represents some volume. And what I was alluding to earlier, the inside limits of integration here, 1 to 3, are telling you what's happening with the inside dx here. So x is going from 1 to 3. And the outside limits of integration go with the dy, so y is going from 0 to 2. So we have a solid where x goes from 1 to 3, y goes from 0 to 2, and the height of the solid, that's what's in the middle here, z equals 4, is a plane that's perpendicular to the z-axis and hits the z-axis at 4, and that's giving you the top of the solid. So if you can picture that, we have y going from 0 to 2, x going from 1 to 3, and z, well, it's going from the xy plane, which is 0 up to 4. So here's a picture. Again, x is going from 1 to 3, y is going from 0 to 2, and z is going from 0 to 4. So this is just a box. We know how to find the volume of a box. We take its length times width times the height, and this is going to be a 2 by 2 by 4 box, so it's just 2 times 2 times 4, or 16. So 16 is the volume that this double integral represents. So the value of this double integral is 16. Let's look at another example. Here, the region is a circle this time that we're integrating in the xy plane. X squared plus y squared equals 9 is a circle centered at the origin of radius 3, and this is the circle and its interior. The height is 1, z equals 1. So again, this is just a plane that's parallel to the xy plane, perpendicular to the z-axis, hitting the z-axis at z equals 1. The picture looks like this. We have a circle in the xy plane, and we're going straight up to the z equals 1, and we're going to have a thin cylinder then of height 1. So the value of this double integral is simply the volume of the cylinder. The volume of a cylinder is pi times the radius squared times the height. So we're going to have pi times 3 squared times 1, and that's going to give us 9 pi. So 9 pi is the value of this double integral. Now, there's something to be learned in this example. When we took z equal to 1, all that's doing is taking the area of what's on the bottom, on the base, and multiplying it by 1 to get the volume. So if we just wanted the area, it's going to be the same thing as this because we just took the area times 1. So if we just want the area, we just put a 1 here, and we're going to end up getting the area of the base of our solid. Let's do one more example. This example is different because I don't have the height being just a constant. Now the height is something different. We are integrating over the same r we had before, the same region in the xy plane, this circle of radius 3 centered at the origin. Let's look at this height function. So z equals the square root of 9 minus x squared minus y squared. Notice that if we square both sides and add x squared plus y squared to both sides, we're going to end up getting x squared plus y squared plus z squared equals 9. So we should recognize that as a sphere centered at the origin of radius 3. So this is just the top part of the sphere because we have a square root there, so we're getting z just being positive here. So we have the top part of the sphere, and we're integrating that for our height, so we're underneath the top part of the sphere and above the xy plane over this circle here. Now notice this circle has the same radius as this sphere, so it's just going to come together nicely, and what we're going to have is a hemisphere, where the base of the hemisphere is the circle that we had here, the x squared plus y squared equals 9, and its interior. And the height, again, is corresponding to this sphere here, or this equation where z is positive. So the volume then is just the volume of half of a sphere of radius 3. So the volume of a sphere is 4/3 times pi r cubed. So we get 1/2 of 4/3 pi times 3 cubed, since 3 was the radius. We can cancel a 2 here, and we can cancel a 3 here, so we're just going to have 2 pi times 9, or 18 pi. So 18 pi is the value of this double integral because that's the volume of the solid that this double integral represents.